Hello friends, this video on DNF block elements part 29 is brought to you by examfear.com. No more fear from exam. There are such compounds also well known for transition metals. Interstitial compounds, transition metals actually are big in size, right? Since they're big in size, so if you keep two balls together or three balls or four balls together and they're big in size, you'll have a lot of voids, big voids. And in these voids, actually small atoms like carbon, nitrogen, oxygen, they can actually be fitted. Carbon, nitrogen, hydrogen, sorry, oxygen is big. Yeah, they can actually fit into these big voids. Now since the transition metals, the actual atomic size is big, right? Big atomic size of transition metal. Since they are big in size, so when you pack them, when you pack these transition metal atoms together, you'll have so many voids. And in these voids, small atoms like carbon, nitrogen, and hydrogen can easily fit in. And this space is called interstitial space. And these elements are called, or these compounds are called interstitial compound. They are not generally non-stoichiometric because they can just lie somewhere here and there. For example, as I told you, TiH 1.7. The next is, how is variability in oxidation states of transition metals different from that of non-transition metals? I told you in transition metals and non-transition metals, both of these shows variable oxidation state, but transition metals, it is more prominent. It is more prominent. We have more and more examples of variable oxidation state in transition metals. For example, Fe2+, Fe3+. Both are very common. Okay, so this is my transition metals. They have non-transition metals also. They have variable oxidation state, but they don't have. They are not that much prominent. And typically, non-transition metals, their oxidation state differ by 2. In this case, there is no such logic. They differ by 1. Now we have to predict which of these will be colored in the aqueous solution. Let's start with titanium with +3 charge. Let's write the electronic configuration of this. It will be A argon 3d1. So 3d1, it has one lone pair electron, thus it will be colored. Okay, unpaired electron imparts color to transition metals. Vanadium with +3 charge, the electronic configuration will be Ar 3d2 actually. In fact, this also has lone pair of electrons, unpaired electrons, so this will also be colored. Cu+, the electronic configuration will be Ar 3d10. It does not have any unpaired electron. If you see 3d10, 1 2 3 4 5 6 7 8 9 10. All the electrons are paired, so it is not colored. Right? Now, scandium with +3 charge, the electronic configuration will be Ar 3d0. Again, this also doesn't have any lone pair of electrons, so it also won't be colored. Mn2+, the electronic configuration will be Ar and 3d5. Again, this has 5 lone pair of electrons, so it will also be colored. Fe+, electronic configuration will be Ar and then it will be 3d5. Sorry, Fe+, 3d. This is Fe+ or Fe + 3? Actually, this is Fe + 3. So Fe3+ will be 3d5. So this will also be colored because it has 5 lone pair of electron. Cobalt with 2+ charge, the electronic configuration will be Ar 3d7, and this will also be actually colored because it has 3 lone pair of electrons. So you can see that. 1 2 3 4 5 6 7. See, 3 lone pair of electrons. Okay, please note that Cu+ ion is colorless. Okay, I'm talking about the Cu+ ions, but when you talk about Cu2O, this is a compound, this is colored, this is red. In fact, Cu2CO3, this is yellow. Cui is brown. So color is actually because of due to transition, and this is in the ions. Okay, please note Cu plus ions are colorless, but actually Cu2 is colored. So using this data, we have to comment on the stability of Fe3 plus ions in the acid solution compared to Cr3 plus or Mn3 plus ions. The data given is to convert Fe3 plus to Fe2 plus, you actually get 0.8 volt of energy. Conversion of chromium plus 3 to chromium plus 2 needs plus 0.4 volt of energy because it is negative here, and Mn3 plus to Mn2 plus also gives 1.5 volt of energy. So we compare in ascending order actually Mn3 plus to Mn2 plus, this gives 1.5 volt energy. Fe3 plus to Fe2 plus gives 0.8 volt of energy, and chromium 3 plus to chromium 2 plus, this needs actually 0.4 volt of energy. Okay, so in that case Mn3 plus is not stable. Why? Because the moment you have Mn3 plus, it will try to convert into Mn2 plus on its own and it will give this much amount of energy. But Cr3 plus is stable because to convert Cr3 plus to Cr2 plus, you actually need this much energy. Okay, so we can say that Fe3 plus is more stable than Mn3 plus, but it is less stable than Cr3 plus. First part is done. The second part, ease with which iron can be oxidized, that means iron can be converted into Fe2 plus as compared to similar process for chromium and manganese. Okay, so iron to iron 2 plus, actually this gives, you see, iron to iron 2 plus will actually gives 0.4 volt of energy, because iron plus to iron, it needs 0.4 volt of energy. So iron to iron plus will give 0.4 volt of energy. Similarly, chromium plus to chromium actually needs 0.9 volt of energy. So chromium to chromium plus will actually give 0.9 volt of energy. Similarly here also, so this gives 1.2 volt, right? Because Mn2 plus to Mn requires 1.2 volt, so Mn to Mn plus 2 gives 1.2 volt. So if we compare these, this is highest. Okay, so ability to get oxides is highest in case of Mn, and then chromium, and then iron, right? Mn, chromium, and then iron. Manganese, chromium, and iron. This is the ability to get oxidized. Okay, so we have to give the reasons for the following. The first one, of the D4 species, Cr2 plus is strong reducing while Mn3 plus is strongly oxidizing. In fact, we have seen this question. Cr2 plus is reducing and Mn3 plus is oxidizing. Oxidizing means it will reduce on its own, it will become Mn2 plus, and Cr2 plus is reducing, that means it will oxidize on its own, it will become Cr3 plus. So if you see the electronic configuration of Cr3 plus, Cr3 plus chromium with 3 plus, it is 3d3, and this is stable by T2G configuration. If you see the electronic configuration of Mn2 plus, it is 3d5, and this is also stable using half filled rule. Both these output are stable, and thus chromium 2 plus is reducing and Mn3 plus is oxidizing. We can also actually answer this question based on the value of E naught. So if we see E naught of Cr2 plus to Cr3 plus is 0.41 volt, and E oxidation of Mn2 plus to Mn3 plus is again Mn3 plus to Mn2 plus. I'm talking here about E reduction because I'm talking about E reduction. This is 1.57 volt. So you see, Mn3 plus can easily reduce and Cr3 plus 2 plus can easily oxidize. So these values are all positive. The next is cobalt is stable in aqueous solution, but in the presence of complex reagent it is easily oxidized. So if we talk about cobalt 2 plus, the electronic configuration is 3d7. Okay. If you want to oxidize it actually to cobalt 3 plus, you need energy. In fact, cobalt 2 plus is stable. Cobalt 2 plus to cobalt 3 plus, you need energy. That is third ionization energy. But in the presence of complexing agent, it actually oxidizes to cobalt 3 plus. Why? Because the amount of energy released by the stabilization of crystals compensates for this third ionization energy. Okay. Next is D1 configuration is very unstable in ions. So if you have D1, it is very unstable. It will try to lose one electron and becomes D0. And this is stable. That means it gets easily oxidized by losing one electron, and thus it is a good reducing agent. Which is the first series transition metal which exhibit plus one oxidation state most frequently, and why? So if you see here, plus one actually is shown only by copper. If you see other, they don't even show plus one oxidation state. So copper shows plus one oxidation state because plus one oxidation state electronic configuration is 3d10 4s0, and this is a stable electronic configuration. Calculate the number of unpaired electrons in the following. Mn3 plus. So Mn3 plus, the electronic configuration will be argon 3d4 4s0. So number of unpaired electrons is 4. Similarly, Cr3 plus, the electronic configuration will be argon 3d3 4s0. Here also the number of unpaired electron is 3. Then we have vanadium 3 plus, electronic configuration is argon 3d2. Here also the number of unpaired electron is 2. And then I have titanium 3 plus, the electronic configuration will be Ar 3d1. Here the number of valence electron will be, sorry, the number of unpaired electron will be 1. So we wanted to find number of unpaired electrons. So Mn3 plus 4 unpaired electron, chromium 3 plus 3 unpaired electron, vanadium 3 plus 2 electron, and titanium 3 plus 1 unpaired electron. Actually you have to find it this way. So for example, yeah, for manganese you have to do like this: 1 2 3 4. It has 4 unpaired electron. For chromium it has 1 2 3 unpaired electron. For vanadium it has again 2 unpaired electron. Titanium it has again 1 unpaired electron. Okay, which among this is the most stable in aqueous solution? If you see, chromium is most stable because others there is no stability factor, but with chromium we have T2G stability factor with T2G configuration. Chromium 3 plus is more stable among all these. Give example and suggest reason of the following features. The first is the lowest oxide of transition metal is basic, highest is amphoteric. The second is the transition metal exhibit highest oxidation state in oxides and fluorides, and the highest oxidation state is exhibited by oxygen in metals. We have to explain this. See, we have already told that the lowest oxides of transition metal is basic and the highest is amphoteric. Why? Because in the lowest oxides, some of the valence electrons are not involved in bonding. Since the valence electrons not involved in bonding, in lowest oxide, some valence electrons are not involved in bonding. They are free and they can donate electron and they behave as base. But higher oxidation state, all of the valence electrons are involved in bonding and they don't have any free electron to donate and they act as acids. Okay. The next one is, for example, I told MnO is basic, and Mn2O7 is acidic. Okay. The next was a transition metal exhibit highest oxidation state in oxides and fluorides. Why? Because oxygen and fluorine has high electronegativity, smaller in size, and thus the transition metals actually exhibit higher oxidation state with these metals. For example, V2O5, Mn2O7. The third is the highest oxidation state is exhibited by oxyanions of a metal. See, oxygen again is electronegative, small in size, plus it forms multiple bonds. Thus, the highest oxidation state is shown by oxyanions. For example, MnO4 minus, here you have +7 oxidation state. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.